This is lecture 8, part 2 for dual theory for IE 3340 operation research. In the first video for this lecture, we discussed the dual, how to formulate the dual given a linear programming formulation. And we also discussed primal dual relationships. We discussed that both the primal and the dual will have the same optimal solution in terms of the objective function. The decision variables are going to be different, but the objective function value is the same at optimality. So we discussed how to obtain the solution of the dual when knowing the optimal solution of the primal. And we presented two methods to achieve that. In this lecture, we're going to focus on the economic interpretation of duality, which is going to help us gather insights about the solutions of our linear programming models. The linear programming problem can be viewed as a resource allocation model that seeks to maximize revenue on their limited resources. Looking at the problem from this standpoint, the associated dual problem offers interesting economic interpretations of the resource allocation model. To formalize the discussion, consider the following representation of the general primal and dual problems. So the general representation basically is the mathematical representation of both the primal and the dual. So we have the coefficients represented by letters. So there's no numbers. And what we can see here are the formulas. So as you can see, if you connect the coefficients, for example, Cj in the primal, they are showing up in the objective function, Cj times xj. And that coefficient, which is the cos, is showing up as the right-hand side of the constraints in the dual problem. Another thing that you can notice is the coefficient bi, which is typically the capacity limitations in the primal, capacity limitations for an operation. So bi shows up in the right-hand side of the constraint, whereas in the dual, that capacity limitation is showing up in the objective function. So as mentioned in this slide, the dual provides some interesting economic interpretations of that resource allocation model that is given by the primal model or the primal linear programming model. So viewed as a resource allocation model, the primal problem has n economic activities and m resources. The coefficient Cj in the primal represents the revenue per unit of activity j. Resource I with availability Vi is consumed at the rate of 8 Aij units per unit of activity j. So Aij shows up in the left-hand side of the constraints. So that's how much of the resource you will need to complete the operation needed for I, or the operation for product or I. So the economic interpretation of the dual variables for any two primal and dual feasible solutions, the values of the objective functions when finite must satisfy the following inequality. So I'm going to write down that inequality. So for Z, which is the objective function value for the primal, this is going to be equal to the summation of j equals 1 up to n Cj xj. And this is always less than or equal to the objective function of the dual, which goes to from I to m bi yi. which is going to be equal to W. So in terms of the resource allocation model, Z represents the revenue in dollars, and BI represents available units of resources, or resource I. Thus, dimensionally, Z equals W. This implies that the revenue in dollars is going to be equal to this objective function value for the dual, which can be expanded or can be represented as follows. This is the same as saying summation from I equals 1 up to M units of resource I times the dollars per unit of resource, in this case, resource I. So this means that the dual variable yi represents the worth per unit of resource I. Okay, so one more time, this means that the dual variable yi represents the worth per unit of resource I. So how can we use this information? So in lecture 8, or the first part of lecture 8, or yes, in this case, this should be a typo. This is sensitivity analysis. We dealt with the sensitivity of the optimal solution. We determined the range for the different LP or linear programming parameters that will keep the optimum basic variables unchanged. In this lecture, we deal with the making changes in the parameters of the model and finding the new optimal solution. So let's look at this example. We have the Toyco problem again, in which this company produces 3 types of toys: train, trucks, and cars. The daily available times for the 3 operations are 430, 460, and 420 minutes. The revenues per unit of toy, train, truck, and car are $3, $2, and $5. The assembly times per train at the 3 operations are 1, 3, and 1 minute. The corresponding times per truck and per car are 204 and 120 minutes. The 0 time indicates that the operation is not used. So we have 3 decision variables, x1, x2, and x3, represent the daily number of units assembled of trains, trucks, and cars. And the associated LP model is given as follows. So we have the maximization of that of the profit that you make for each one of those products. And then we have the limitations for each one of the operations. So we have some time limitations. These are how much of how many units we have of each one of the operations. And these are the amounts that are needed per product of these operation. So this is our formulation, and using x4, x5, and x6 as the slack variables for the constraints of operations 1, 2, and 3, the optimal tableau after applying the simplex method is shown here at the bottom of this slide. So we have that we have three basic variables, x2, x3, and x6, and these are the values. So in this problem, x1 is equal to 0. So you are not producing trains. X1 is equal to 0 because it's not part of the basics. So if it is a non-basic variable, the value is equal to 0, x2 equals 100, and x3 equals 230. So even though you're not making as much profit with x2 as compared to x1, I'm sorry, you're still not producing product one. Okay, so there has to be a reason for that. And the reason is connected to the amount of resources that you need per operation. So if this producing product one costs you more than what you get in terms of revenue, then the model will tell you, no, you should not produce that product. So how many trains? Is 0. How many trucks? 100. How many cars? 230. So this is X1, this is X2, and this is X3 at optimality. And the profit that you are making, so Z equals $1,350. So we want to formulate the dual for this problem. So here I'm going to state that. So the dual is going to be minimization. Minimize Z equals, sorry, this should be W. W equals 430 times Y1 plus 460 times Y2 plus 420 times Y3. So remember, we assign a dual variable to each one of the constraints, and then we proceed as explained in the first video. So this should be Y3. And this is subject to the following: Y1 plus 3Y2 plus Y3. Sorry, should be just Y3 plus Y3 should be greater or equal to 3. 2Y1 plus 4Y3 should be greater or equal to 2. Y1 plus 2Y2 should be greater or equal to 5. Y1, Y2, and Y3 should be greater or equal to 0. So by applying one of the two methods that we discussed at the end of the previous video, we can find the optimal solution for the dual. So the optimal solution equals Y1 equals 1, Y2 equals 2, and Y3 equals 0. And if we substitute these values into the objective function, that is 430 times Y1, which is equal to 1, plus 460 times 2, and that is equal to $1,350. Okay, so you can see that the objective function value for the dual problem is the same as the objective function value at optimality for the primal. So let's talk about the changes affecting feasibility. The feasibility of the current optimal solution is affected only if the right-hand side of the constraints is changed. This change requires recomputing the right-hand side of the tableau using the following formula. The new right-hand side of the tableau in iteration I is going to be equal to the inverse in iteration I times the new right-hand side of the constraints. Recall that the right-hand side of the tableau gives the values of the basic variables. So suppose that Toyco is increasing the daily capacity of operations 1, 2, and 3 to 600, 640, and 590 minutes, respectively. How will this change affect the total revenue? So with these increases, the only change that will take place in the optimal tableau is the right-hand side. Of the constraints. Okay, so if we look at the optimal solution of this tableau, we can identify the inverse. This is our inverse, and we can identify our basic variables. So the only thing that we are changing is this right-hand side, and we want to find how would this change affect the total revenue. So if we go back here, the new right-hand side of the tableau in iteration I is going to be equal to the inverse in iteration I times the new right-hand side of the constraints. So that's what we're going to use to find the impact. So what will be basic variables based in that optimal tableau? X2, X3, and X6. The inverse, as stated in that optimal tableau, is 1/2 minus 1/4, 0, 0, 1/2, 0, minus 2, 1, and 1. And the new right-hand side is given by these values. So this is 600, 640, and 590. So the multiplication of these two, this matrix and vector, will give us the following: 140, 320, and 30. So the current basic variables x2, x3, and x6 remain feasible. The associated optimal revenue is going to be the following. So let me make that note. The current basic variables x2, x3, and x6 remain feasible because they are positive. Okay, so the associated optimum revenue is then you're gonna use these values. So I have x2 and x3. So I'm going to substitute that since x1 into the objective function z. So x1 is 0, so it's 3 times 0 plus 2 times x2, 140 plus 3, I'm sorry, plus 5 times x3, which is 320. And the new objective function value will be 1,880. So you can see that by making or by increasing the amount of time and making these computations, we can see that the increasing time for each one of those operations is increasing the revenue. Originally was 1,350, now is $1,880. Let's look at a different situation. Although the new solution is appealing from the standpoint of increasing revenue, Toyco recognizes that its implementation might take time. Another proposal shifts the slack capacity of operation 3. If you see x6 in the basics is equal to 20 minutes, so there's some slack there. So they're saying let's move that slack, those 20 minutes, to the capacity of operation 1. How would this change impact the optimal solution? So the capacity mix of the 3 operations changes to 450, 460, and 400 minutes. Since we move some of those 20 minutes from operation 3 to operation 1. So if you remember in the original problem, these were the values. So what we did was we took 20 minutes from here and we added that to operation 1. So that's why we get these values, 450, 460, and 400 minutes, respectively. The resulting solution is, so as we did for the previous example, we have our basic variables, x2, x3, and x6. And then we're going to multiply that by the inverse in the optimal tableau. So 1/2 minus 1/4, 0, 0, 1/2, 0, minus 2, 1, and 1. And times the new values for the right-hand side, which are 450, 460, and 400. And this multiplication will give us the following: 110, 230, and minus 40. So what happens here is that we have a negative value here, which means that this resulting solution is infeasible. So the resulting solution is infeasible because x6 is less than 0. Okay, So what this means is that these changes are not providing us with a optimal solution in which x2, x3, and x6 are basic variables. So changes affecting optimality, consider making changes in the objective coefficients now. These changes affect only the optimality of the solution and requires recomputing the zero coefficients or the reduced cost as according to the following procedure. First, we're going to compute the dual values, and then we're going to substitute the new dual values to determine the new reduced cost or zero coefficients. So let's look at this situation. In the Toyco model, suppose that the company has a new pricing policy to meet the competition. The unit revenues are 2, 3, and 4 for train trucks and car toys, respectively. So we are changing the prices, selling prices for these products. So the new objective function is the maximization of z equals to 2x1 plus 3x2 plus 4x3. So we have a new objective function. We remember the original objective function has 3, 2, and 5 as the coefficients. So those prices are being changed in this example. So now the new prices are 2, 3, and 4. So we need the dual values as explained in the previous example. So using method 2 explained in the previous video to obtain dual values. Okay, so we want to find y1, y2, and y3. So this is going to be equal to, remember that we used the order of the basic variables, right? So if you remember, the order of the basic variables are x2, x3, and x6. So in here, we use 3 and 4. 6 has no values in the objective function. So it's 3, 4, and 0 times 1/2 minus 1/4, 0, 0, 1/2, 0, minus 2, 1, and 1. So the dual values are 3/2, 5/4, and 0. The objective zero computations. In any simplex iteration, an iteration of the simplex algorithm, the objective coefficient for the reduced cost of xj is computed as follows. So the equation is primal z equation coefficient of xi. So the primal z equation coefficient of xi is going to be equal to the left hand side of jth dual constraint minus the right hand side of the jth dual constraint. So it is not necessary to recompute the objective row coefficients of the basic variables x2, x3, and x6 because since they are basic, they are always zero. In row 0, in the tableau, the basic variables are going to be 0 because they are part of the identity matrix. So we just need to find the reduced cost for the variables that are not basic. So the reduced cost of x1 is going to be y1 plus 3y2 plus y3 minus 2 has to be equal to 13/4. The reduced cost of x4 is going to be equal to y1 minus 0 equals 3/2. And the reduced cost of x5 is going to be equal to y2 minus 0 equals 5/4. Since all of them are greater or equal to 0 to reduce costs, then what that means is that the current solution remains optimal because all the reduced costs are greater than 0, and the new objective function value is going to be equal to 2 times 0 plus 3 times 100 plus 4 times 210, which is equal to $1,220, which is not better than the original objective function. So making changes in the, or making these changes in the pricing is not giving you a better solution or better revenue. Suppose that the Toyco objective function is now changed to the following: 6x1, 3x2 plus 4x3. So the question is, will the optimum solution change? So we are going to follow the same process as we did on the previous example. So we have y1, y2, which are the dual variables that we are going to compute based on the optimal solution for this problem, or the primal. So we follow the same process. And we get, so this is 1/2 minus 1/4, 0, 0, 1/2, 0, minus 2, 1, and 1. And this is equal to 3/2, 5/4, and 0. Okay, so we have the same solution for the dual variables, 3/2, 5/4, and 0. So we now compute the reduced cost for the non-basics. So the reduced cost of x1 is going to be equal to y1 plus 3y2 plus y3 minus 6 is going to be equal to 3/2 plus 3 times 5/4 plus 0 minus 6, and this is equal to minus 3/4. The reduced cost of x4 is going to be equal to y1 minus 0, which is 3/2. So that's how we got this value. And then reduced cost of x5 is going to be a y2 minus 0, which is 5/4. And so we knew that. So what happens here is that this value is negative. And what that means is the new reduced cost of x1 shows that the current solution is not optimal. Okay, so we will have to solve the problem again. We cannot take this shortcut to evaluate the optimal solution of the problem. Okay, so that concludes this lecture. So in this lecture, we discussed the definition of the dual problem. We discussed the primal dual relationships. We discussed the economic interpretation of duality. And also we discussed post-optimal analysis using dual theory.